Yeah, thank you. So I wanted to give this short talk. I was inspired by Marina's talk this morning. I also work with the Hitchin vibration in a slightly different context. So I wanted to introduce a bit of that kind of framework and say something about what that landscape looks like for me. So let's let X be a curve over a field. Generally, I want it to be FQ or FQ bar because I have in mind taking some trace of Frobenius down the line. Everything I say will be true for over C and generally easier to prove, so it's pretty okay for the geometric purposes. And the sort of object that I'm interested in are reductive group schemes over the curve. So reductivity is a property on geometric fibers. So what you should picture here is that this is something like a matrix group, like a GLN, but twisted globally over the curve. So I'll give a primary example. If I had, say, in a tall double cover of my curve, then I could consider the unitary group associated to this double cover. There's several, but I'll say the quasi-split one, which is contained in the Weil restriction of GLN X prime. And what is it? Well, it's the unitary matrices, right, in a usual sense. So it's the sections of GLN over the bigger curve that preserve a Hermitian form on the structure sheaf. So something like this, where this is some matrix like maybe this one, or you could make it diagonal if you prefer. I want the quasi-split one. So yeah, how should you think about this thing? Well, this thing, if I were to base change it, it's a group scheme over X. If I were to base change it to X prime, I would just get GLN. This is a Galois twist of GLN. You should picture a bunch of GLNs where you've glued it over the monodromy of this double curve along the inverse transpose map is the map that defines this one. And if you looked at the generic points, if I wrote the function fields F prime and F here, then this would just be a unitary group associated, this quadratic extension of fields. So these are the kinds of geometric objects I'd like to study. And all of the formalism of the Hitchin vibration transfers perfectly well to groups like this. So I'm going to fix a very positive divisor. It's going to absorb both the K and the D from Marina's talk, because the K is not so important for my purposes. Then there is a Hitchin vibration. The total space M consists of G torsors over X and a section of what I'll call an adjoint bundle twisted by D. So what does this mean in practice, or in an example like this? This is going to be a unitary bundle. So for example, E could be, for this group, it would be a vector bundle not on X, but on X prime, along with an isomorphism, maybe I'll call it H, to the conjugate transpose of the vector bundle, aka a perfect pairing between it and its conjugate dual. So that's the data of a unitary torsor. And then the theta is, well, sorry, what do I mean? It's just going to be an endomorphism that is compatible with sort of duality under this. Endomorphism such that, maybe I'll say, it should be skew symmetric in the usual Lie algebra sense. So something like this. Okay, and if you have something like this, it still makes perfect sense to take its characteristic polynomial. Maybe I won't bother saying precisely what the downstairs space is, but there's still some affine space, and you can take a characteristic polynomial and it'll be naturally valued in some space of global sections of some bundles. Okay, so why do I care about a Hitchin vibration like this? Well, as Marina was saying, this thing is, if you work over a nice enough locus of the base, then this thing becomes basically an abelian variety, up to some Artin stackiness and some connected components. Over this, know, and in characteristic 0, others knew earlier, that this is a very nice variety. The instant you leave this locus at all hell breaks loose. So for example, the simplest non-elliptic fibers that you can write down for the Hitchin vibration for GL2 is an infinite chain of P1s with 2 doubled points, where the doubled points are connected in a chain. Horrifically non-separated, horrifically infinite type. And so a big question is, how can we get a handle on the Hitchin fibration over this slightly larger locus? The answer, it turns out, is exactly to impose stability conditions. So far, I've imposed no kind of stability or semi-stability conditions. But the insight of Chaudard and Lamont was that the complement of this locus is in some way controlled by bundles that admit parabolic reductions, that admit stable subspaces. And so you can impose a stability condition for each parabolic reduction. Stability condition for each p reduction that a particular bundle admits. And so you change nothing over this locus, but you can truncate this Hitchin fibration sort of in the fiber direction to get something that's well behaved over a larger locus. In particular, the goal, and maybe I'll say it as a work in progress, is that in this generality, if we perform this truncation, we get something. It's defined over the whole Hitchin base, but over what I'll call maybe the generically regular semi-simple locus is a proper Deligne-Mumford stack. You can get rid of at least the worst aspects of the infinite type and the non-separatedness. Why do we care? This is exactly the kind of framework where you can apply the decomposition theorem of BBDG. So this allows us to then, work with the constructible derived category and be able to adapt cohomological arguments for things like trace of Frobenius.